Hi, everybody. Researching iOS internals and iOS vulnerabilities is hard, right? You know what I mean. My name is Jonathan Afek, and welcome to the talk, Simplifying iOS Research, Booting the iOS Kernel to an Interactive Bash Shell on QEMU. I'm very excited to be here and present this project to you. I want to thank you all for being here and for attending this talk with me. Let's begin. In this talk, I will present a new simple way to research iOS. Before we get to this new way, let's review the current research methods. So what are the current research methods researchers use in order to analyze iOS? There's a company which offers full iOS emulation on the remote servers for their customers. They have full debug capabilities, they offer many research features, and they have a solution for many iOS versions on many iOS devices. This sounds great, right? Well, it is great, but there are a few issues with using it. The first one is that you must be invited. It is not generally available. The second issue is that it costs a lot of money to use their services. But most importantly, your private research, which possibly contains sensitive research details and vulnerabilities, is exposed to anyone who can get access to the servers. Another method used by researchers is to use development-fused iPhones. Now, these are iPhone devices made by Apple with full debug capabilities used by their own OS developers so they could be able to debug their code on real iPhone devices. Recently, Apple also announced that they're going to provide such devices to a select few non-Apple iOS researchers in order to assist uncovering iOS security vulnerabilities before they are used by offensive hackers. This is also great for research if you can get your hands on such a device, but unfortunately, it is very much unavailable. It is very hard to get a device. And even if you do get one, you probably had to do something illegal or at least make an Apple employee perform a serious breach of contract in order to get one. And the third issue is that it doesn't scale well to use physical devices for research, especially if these devices are very, very hard to get. Another method used by researchers is to use jailbroken devices. Now, on jailbroken devices, you can execute arbitrary kernel code, and recently Brendan, Azad, and Ian Bear published projects which enable debug capabilities on some iPhones using vulnerabilities. This is also great for research, but unless you use this new kernel debugger, then executing kernel code is far from full debug capabilities on an emulated device. You cannot perform research on multiple iOS versions, as these devices can never be downgraded, and most of the time you can only upgrade to the latest iOS version if you want to upgrade at all. So it is hard to conduct a multi-version research using this approach. It is also more challenging to scale such research while using physical devices. And most importantly, it requires a vulnerability to jailbreak the iPhone or to use this new kernel debugger. So in most cases, it cannot be used to research the most recent iOS on the most recent iOS device. Another method used by researchers is to use regular iPhones, non-jailbroken iPhones. These iPhones are very easy to get. You can just buy them at the store. But they're very limited in their debug and research capabilities. In most cases, all you have is a crash report that looks like this. Now, this gives a lot of information regarding the status of the CPU and the registers when the panic happened or the vulnerability was triggered. But it is still very hard to work with, and it is much more difficult than working with a full kernel debugger on an emulated system. My goal in emulating iOS was to create a new, open, free, easy-to-use way to privately research iOS without requiring any vulnerabilities, and it only takes about 5 minutes to start using it. Emulation lets you have full debug capabilities. It is easier to develop support for more iOS versions, and you can run multiple instances easily at scale for debugging, research, and fuzzing. Before we get to the research details, let me tell you a little bit about myself. So my name is Jonathan Afek, and I manage the Aleph research group at HCL AppScan. When I started this role, I wanted to start getting into iOS security research. While studying the subject, I realized that there was no good, public, open way to research iOS internals and vulnerability. This is when I started looking into emulation. I thought that if iOS could be executed on QEMU, then I could create such a way and enable such research. I looked it up to see if anyone started working on emulating iOS and found a few very old projects that are not relevant for current versions. I also found another project that started working on executing iOS on QEMU and reached some very interesting milestones. Now, this is the amazing work I found posted on the Worth Doing Badly blog by Mr. Chung. So for anyone not familiar with QEMU, QEMU is a free and open source emulator that supports emulating ARM64 architectures, and it is a great project to start from when trying to emulate iOS devices. Before we get to our research, let's see what was achieved by Mr. Chung's project. So they chose to work on iOS 12 Beta 4 for iPhone 10. They were able to extract the kernel image and the device tree from the software update freely available on Apple servers. They were able to patch the kernel and the device tree and load them both and the kernel boot arguments into the emulated device's memory. They were able to extract the RAM disk from the software update and also load it into the emulated device's memory. They were able to emulate a UART serial device connected to the emulated iOS host and achieved serial output only, no serial input. They were able to boot the kernel on QEMU up to the point where it executed the first user mode application, launch D, the first user mode process, though no applications that are not signed by Apple were executed on their system. Here you can see the system's serial output, and in the output you can see that launch D was actually executed and produced output. So what were our goals when starting this project? We wanted to boot iOS on QEMU without patching the kernel at all. We wanted to support different hardware devices, disk, display, touch, sound, and everything else. We wanted to support different iOS versions for different iOS devices. And of course, the main motivation for starting this all was to conduct iOS security research using this project. And we wanted to learn a lot about iOS and QEMU internals while working on the project. So what is the current status of our project? We're currently able to boot the secure monitor and the kernel both unpatched on QEMU. We're able to execute user mode processes, our own user mode applications that are not signed by Apple over launchd. We're able to run an interactive bash shell on iOS on QEMU. And we currently only support iOS 12.1 for iPhone 6s Plus. All right. Then now, let's see a short demonstration of our project before we talk about the research details. All right, so this is the command line we execute in order to execute our modified QEMU to emulate iOS 6s Plus. So now let's fire up GDB and attach it to the QEMU instance and continue execution. Now here you can see the kernel boot messages, and we have an interactive bash shell. Now let's update the path environment variable to point where all our executables reside. We can see that we have an interactive bash shell running as root. We can extract some host information. We can extract information about the loaded kernel extensions. We can extract some virtual memory statistics. We can get some more host information. We can extract the full IOKit registry. But most importantly, we can just break the execution of the kernel in GDB and debug it in GDB with all the familiar and known GDB features in a regular and known GDB session as you would debug anything else in GDB. All right. So we talked about interesting past research done for executing iOS on QEMU. In this talk, we're going to walk through some select research stages we had to go through to achieve iOS execution on QEMU. We will first talk about how we were able to boot the kernel, then talk about how we were able to run executables that are not signed by Apple on the emulated iOS device. After that, we will talk about how we executed bash on iOS, and then about how we were able to get interactivity with the executed bash process. And finally, we will talk about what lies ahead for this project. All right, then how did we boot the iOS kernel on QEMU? We started off with the method used by Mr. Chang's project. We loaded the different sections of the kernel into the emulated device's memory and started executing the kernel at its entry point in exception level 1. But soon enough, we hit a crash on the first secure monitor call instruction. So what is a secure monitor? Somewhat similar to the protection rings concept in x86, in ARM we have 4 exception levels. The user mode code runs in exception level 0. The kernel runs in exception level 1. We don't have code for exception level 2 in our system, but it is used for hypervisors. And the secure monitor runs in the most privileged mode, exception level 3. Now, this is how the secure monitor works on iOS. Well, the secure monitor is the first thing that runs after the bootloader, and it starts its execution in exception level 3. It resides in a secure memory location that is inaccessible from other exception levels, including the kernel that runs in exception level 1. It is used to service secure monitor calls from the kernel, somewhat similar to how the kernel services system calls from user mode code. It is responsible for KPP, kernel patch protection. This is a mechanism that protects the kernel code. Even if a hacker has an arbitrary write exploit in the iOS kernel memory, then they are not able to override the kernel code as it is protected by KPP. So why did this approach work for Mr. Chang's project and not for us? Why were they able to just load all the different sections of the kernel and start execution in exception level 1 when we couldn't? We encountered an error while executing the secure monitor call instruction. Well, they actually used an iOS version for iPhone 10, and iPhone 10 uses a different mechanism to prevent patches. It uses KTRR, and it does not use a secure monitor to implement KPP. Now, this means that the iOS version for iPhone 10 does not use secure monitor call instructions, and therefore they do not need to execute a secure monitor in order to service the secure monitor calls. Now, the reason we chose this iOS version for iPhone 6s Plus is that it is the only iOS 12 version that we know of that Apple released with kernel symbols in it. And that makes reverse engineering and working on this project much simpler. All right, so we see that the kernel now needs the kernel needs a secure monitor to service its secure monitor calls. So any ideas how we can solve this and continue with kernel execution? So what we did was actually extract the secure monitor image from the software update and load the secure monitor image and the secure monitor boot arguments in the emulated device's secure monitor and start executing it at its entry point in exception level 3. All right, so were we now able to boot the kernel using this approach? Well, we started executing the secure monitor code, but soon enough we encountered a data abort exception. This happens because the secure monitor, in order to implement KPP, needs information about the different kernel sections so it can know what sections need protection and where they are loaded in memory. The secure monitor gets this information from the kernel's Maho header. But it seems that the secure monitor looks for this header in a location where it is not found, and therefore it triggers the data abort exception. Now, here you can see a snippet of code of the secure monitor code where it parses the kernel's Maho header and searches for a specific kernel section called text exec. So this is the layout of how we loaded the different kernel sections. So we just loaded all the different kernel sections to where they're supposed to be in memory. And you see that we have some kernel sections that are loaded below the kernel Maho header. Then we have the kernel Maho header loaded. Then we have some sections that are loaded above the kernel Maho header. And we also have the base address boot argument. Now, we pointed the base address boot argument to the lowest loaded kernel address based on the work done by Mr. Chang. And it turns out that the secure monitor actually tries to find the kernel Maho header based on the base address boot argument. So this is the place where the secure monitor tries to find the kernel Maho header. And since it currently does not point to the kernel Maho header, then we get this data abort exception. All right, so we saw that the kernel needs a secure monitor to service its secure monitor calls. So we loaded the secure monitor and started executing it. And we saw that the secure monitor requires the base address boot argument to point to the kernel macro header. Any ideas how we can solve it and continue with kernel execution? So we tried to do a few different approaches, and after a few attempts, we tried this solution. So this is a basic solution, right? Just make the base address boot argument point to the kernel macro header instead of the lowest loaded kernel address. So are we now able to boot the kernel using this approach? So it got us a little bit further, right? Now we're able to execute the full boot sequence in the secure monitor and actually get to kernel execution in exception level 1. But after getting the kernel execution, after starting executing the kernel itself, we get to this function. Now this function, the static v2p, gets called a lot in the kernel. It is a kernel function that is used a lot. And in the circled line, you can see that it uses a global variable called gvirt_base. Now, this gvirt_base global variable is based on the base address boot argument. Whatever value we put in the base address boot argument goes into the gvirt_base global variable. And you can see that if VA, the input virtual address to this function, is lower than gvirt_base, then we get a negative number in this subtraction. Now, if this negative number is treated as an unsigned integer, then it is a very large unsigned integer that is larger than the physical memory size. Then, therefore, this condition is true, and we get to the next line, which is a panic line, and we get a kernel panic. So we need to make sure that this function never gets called with a VA with a virtual address that is lower than gvirt_base. So in order to do that, we need to make sure that gvirt_base points to the lowest loaded kernel address. So we saw that the kernel needs a secure monitor to service its secure monitor calls. So we loaded the secure monitor. But we now see that the secure monitor requires the base address boot argument to point to the kernel macro header. And we have another requirement for the base address boot argument. We see that it needs to point to the lowest loaded kernel address. So any ideas how we can solve that and continue with kernel execution? So after a few attempts, we actually tried this solution. So we stayed with all the loaded different kernel sections. We loaded them to the same place, but we also added into the emulated device's memory another copy of the raw kernel file that we extracted from the software update. And this raw kernel file begins with the kernel macro header. So what we did was point the base address boot argument to this new copy that is loaded below the lowest loaded kernel section. So now we have the base address boot argument pointing to the kernel macro header, and we have it pointing to an address that is lower than the lowest loaded kernel address. And now it works, and we're able to boot the kernel up to the point where it executes launchd, the first user mode application. All right, so we're now able to boot the kernel. Next, I want to talk about how we were able to make the iOS kernel execute our own executables, right? Because the iOS kernel doesn't allow execution of executables that are not signed by Apple. So let's see how we got the iOS kernel executing our own executables that are not signed by Apple. In order to do this, we used a trust cache. So what is a trust cache? Trust cache is a list of executable hashes that represent the executables that are allowed execution in iOS without a signature verification. Only if the executable hash is not in the trust cache, then its signature is checked. If it is in the list, then execution is allowed. So let's see how this works by a simple example. So let's say we try to execute executable 1 with hash 34CB on the iOS kernel. Let's say the blue boxes represent the trust cache. Now the kernel tries to find this executable hash in the trust cache, and it is unable to find it there. And then it tries to verify the executable signature. And since it is not signed by Apple, then execution is denied. Now let's say we try to execute executable 2 with the hash 1EC4 on the iOS kernel. And this time the kernel is able to find it in the trust cache, and therefore execution is allowed. Now the iOS kernel supports 3 different types of trust caches. The first one is a list of hard-coded hashes that are hard-coded into kernel code itself. Now we could actually override this list with our own hashes and make the kernel execute our own executables. But we did not want to patch the kernel at all, therefore we did not use this approach. The second type of trust cache that is supported by the iOS kernel is a dynamic trust cache that can be loaded at runtime. Now, in order to execute the code that actually loads this trust cache from a file, we need to first be approved for execution on the iOS system. And therefore, we cannot use this approach. And then the last type of trust cache that is supported by the iOS kernel is a static trust cache that is placed in memory before the boot sequence, and it is pointed to from the device tree. So what is a device tree? A device tree lets the bootloader tell the kernel what hardware devices are attached to the host and the specifications of these devices. In addition, it enables the bootloader to pass to the kernel other pieces of information, such as the location in memory of the static trust cache. Now, the raw device tree is available in the software update. We do patch the device tree to add the static trust cache to it, and we also patch it for different reasons. But it is very different from patching the kernel, as it is a structured description of devices, and it is easier to parse and edit for supporting different iOS versions, as opposed to searching for specific code locations in the kernel code to patch that frequently change in different iOS versions. Now, this is the top-level core trust validation code. Now, this code in the iOS kernel is responsible for searching for the executable hash in the 3 types of trust caches. And if it is unable to find it there, then it goes on to signature verification. And if we dive deeper into the static trust cache lookup, we get to this function, lookup in static trust cache. Now, if this function is able to find the executable hash in the static trust cache, then execution is allowed. Now, using cross-references, we can see that this is the code that actually builds the static trust cache that is later used by the lookup function. Now, this code parses the input structure that is pointed to from the device tree and builds the new structure that will later be used by the lookup function. Reverse engineering the function that we just saw before reveals that this is the input structure that is expected to be the static trust cache to be in. Now, we will not go into all the details of this structure, but the important thing is to know that it enables us to build our own static trust cache and use our own hashes inside this new static trust cache, and therefore make the iOS kernel allow execution of our own executables. Now, using cross-references, we can see that the memory address of this structure, of this input structure, is actually read from the device tree. And good thing that this code is actually open source, so here you can see where the kernel fetches from the device tree the memory address of the static trust cache. All right, so did that work? Are we now able to make the iOS kernel execute our own executable? Well, it sort of works. It always worked when we used only one hash in the static trust cache. But when we tried to use more items in the static trust cache, when we put more hashes in the static trust cache, then some executables worked and some executables were denied execution. Now, any ideas why this happened or how we can solve it? Well, reverse engineering the lookup in static trust cache function actually revealed that it implements a binary search algorithm. And a binary search algorithm expects a sorted list. So now all we had to do was sort the hashes in our static trust cache, and now it worked. Now we're able to make the iOS kernel execute our own executables that are not signed by Apple. All right, so we're now able to boot the kernel, and we're able to make the iOS kernel execute our own executables. Now let's see how we made launchd that is already executed execute our bash process, our bash shell. So the method to do this was simple. First, we mounted the ROM disk that is later used for the QEMU execution. We mounted it on our research computer. And we removed all the files from the launch daemons directory. Now, this directory is responsible for holding each one of the files in this directory is responsible for instructing launchd to execute a different process, daemon, or service on the iOS system. And we wanted to just execute the bash shell without interference. We didn't want anything else to interfere, and we wanted to just execute bash. So we removed all the files that existed in this directory. And we added a single file to this directory, a file that instructs launchd to execute our bash shell. And we copied the bash executable to the ROM disk. And we added the bash executable hash to the trust cache. and we unmounted the ROM disk and started QEMU. Now this is the file we put in the launchd directory that instructs launchd to execute our bash shell. Now here you can see we instructed launchd to start the bash shell interactively. And here we pointed launchd to where you can find the bash executable on the ROM disk. And here we instructed launchd to use /dev/console, which is the serial device, as stdout, stderr, and stdin for the bash shell. And here we instructed launchd to execute the bash shell as root. Now, did that work? Were we able to execute the bash process now? Well, the logs show that there are missing libraries required in order to execute bash, so it did not work at first. Now, any ideas why this happened or how we can solve this? Well, it turns out that the ROM disk image comes without the dynamic loader cache file on it. This file holds the most common runtime libraries for iOS, and it is required in order to execute a lot of processes, including bash. So we tried a simple solution. We have the full disk image from the software update, so we just copied this dynamic loader cache file from the full disk image into the ROM disk at the correct location and executed again. But alas, it still did not work. We got the same error. Now, any ideas why this happened or how we can solve it? So in order to understand this issue, we started debugging the dynamic loader, which is the user mode code responsible for loading the dynamic loader cache file. Now, since we have GDB attached to our QEMU instance, we can actually debug the code that is running on it. So good thing that the dynamic loader is open source, so we can just start debugging before the call to the function open shared cache file, which is responsible for loading the dynamic loader cache file. And stepping through execution, we saw that what actually fails is the call to this system call, shared reach and map and slide. Now, since the project we developed has a kernel debugger, then it makes what would otherwise be a great challenge very simple. We can just debug the user mode code and continue debugging the kernel through the system call. And debugging the system call, we see that what actually fails is this function call, shared reach and map and slide. And inside this function call, we can see that the condition that fails is this condition. And we see that it expects the dynamic loader cache file to be owned by UID0, to be owned by root. So we now see that in order to load the dynamic loader cache file, we need it to be owned by root. So the solution was simple. We just mounted the ROM disk in a different way, right? Because the default way of mounting the ROM disk on the research computer does not allow permission editing on the ROM disk. So we mounted it on the research computer in a different way, which does allow permission editing. And we copied the cache file and owned it to root. And now it works, and we have bash executed on our system. So we're now able to boot the kernel. We're able to make the iOS kernel allow execution of our own executables, including bash. And we're able to make launchd execute our bash process, our bash shell. But since we're based on Mr. Chung's project and he achieved only a serial output, then we now have a bash prompt on the serial output. But we're not able to interact with it, right? We just see the bash prompt, but we're not able to input anything into the bash shell. So how did we get interactivity with the bash shell? How did we enable serial input? So reverse engineering the kernel revealed that actually this is the location where serial input is decided upon. This is where, if this branch is taken, then serial input is enabled. So we see that if the W8 register bit number 1 is on, then serial input is enabled. And further reverse engineering the kernel actually revealed that the value of W8 in that location comes from the kernel boot argument, the kernel serial boot argument. So all we had to do was set the serial boot argument to 2, which means bit number 1 is on, and then we have serial input, and we have an interactive bash shell. All right, so some of you may be familiar with the voucher swap vulnerability research that was published by Brendan Azad. It did an amazing work exploiting this vulnerability, and it is a subject for a full-length talk on its own. This vulnerability was used to jailbreak iOS 12.1. I'm not going to go through all the details of exploitation, but I do want to show you, as a demonstration of research, how simple it is to trigger this vulnerability on this project and see exactly what goes on in the kernel while this vulnerability is triggered, using this project's debug capabilities. I will also demonstrate some helpful for research GDB scripts that were written by our very own Aleph security researcher, Vera Menz. All right, so this is the code that we're going to compile and execute, the user mode process that we're going to compile and execute on our project in order to trigger the voucher swap vulnerability. Now, in order to understand this vulnerability in this code, we need to understand something about vouchers. Now, vouchers are kernel objects that are reference counted. When a voucher is created, a machboard is also created that references it, and therefore it has a reference count of 1. And vouchers can also be assigned to threads. So when a voucher is assigned to a thread, then the thread also references the voucher, and its reference count is increased. So what does this code do? Well, first, we create a new thread. So we have a new thread in this process. Then we create a voucher. And when we create the voucher, we also create a machboard that references the voucher, so the voucher has a reference count of 1. And then we assign the voucher to the thread. So now the voucher has a reference count of 2, right? 1 reference from the machboard and 1 reference from the thread. Then we call the voucher release function. Now, in this function, we call the voucher swap function, which triggers the vulnerability. Now, this vulnerability actually decreases the reference count of the voucher by 1. So it now has a reference count of 1 instead of 2. But it still has 2 live references, 1 from the machboard and 1 from the thread. So the next thing we do is destroy the machboard. So the reference count goes down again from 1 to 0. And the voucher is deallocated and its memory is freed. But it still has a live reference from the thread. So the next thing we do is actually try to fetch the voucher from the thread. But since the voucher was already deallocated, the iOS kernel code that fetches the voucher from the thread tries to verify that the voucher is valid. And because it is no longer valid, then we get a kernel panic, and we get a use after free vulnerability triggered here. So now let's see this in action. All right, so we now execute our process that triggers the vulnerability. So this is one of the scripts I talked about. This is a script that parses the global threads list in the iOS kernel and actually displays all the user threads that are currently running in the system. And we can see that our process is running. The voucher swap process is currently running, and it is now at thread create, at the beginning of the function thread create. This is our first breakpoint. So let's continue execution. And now we're at the end of the function thread create, and we can see that actually a new thread was created for our process, for the voucher swap process. And this is another very useful script. Now, this script actually parses the struct thread of every thread we give to it and displays a lot of useful information about the thread. So let's see the information about the newly created thread. And here we can see that the ith voucher member is currently 0, right? Because we stopped just after creating the new thread. So it currently references no thread. It doesn't reference any thread, so the ith voucher member is now 0. Now let's continue execution. Now this breakpoint is just after creating the voucher and assigning it to this thread. And now we can see that the thread, actually the ith voucher member of the thread, is no longer 0. It now references the voucher. And another useful script is this script, which parses the voucher object itself. Now, if you look at the third member from the top, ivrefs, you can see the reference count is now 2, as expected, right? Because we have 1 reference from the machboard and 1 reference from the thread. So we have a reference count of 2. All right, so now we're stopped just after triggering the vulnerability, and we see that the reference count is now down from 2 to 1. Now, let's continue. And we're now stopped just after destroying the machport. So we now see that the reference count is down again from 1 to 0, and the voucher is freed, and its memory is freed. And we can see that the first 8 bytes of the voucher are actually now a pointer value that points to the next free buffer in the voucher allocation zone. But we can also see in the thread information that even though the voucher was deallocated, the thread still references the voucher. So now when we continue execution and try to fetch the voucher from the thread, we expect a kernel panic because the voucher is no longer valid. And indeed, we got a kernel panic, which says OS reference count used unsafely when 0. All right, so this was a demonstration of how simple it is to research vulnerabilities, some vulnerabilities using this project. So we talked about some select research stages we had to go through in order to implement this project. Now let's see what's next for this project. So one of the things we want to implement is to implement IP communication. Currently, we interact with the guest only through the serial interface. But we want to connect to it using SSH to have a richer shell experience and to be able to copy files to and from the guest system. We want to support non-RAM disk disks. This is because currently the RAM disk that is mounted as the root mount on the guest system is by default mounted by the iOS kernel as read-only, and we want to have a read and write root mount. And also, it is limited in size, and we want to have more data and files on the root mount. And also, it is very wasteful in resources for the host computer. So, for these 3 reasons, we want to have non-RAM disk support. We also want to have more hardware devices. We want to support more hardware devices, disk, string, touch, sound, and everything else. We want to load all the regular iOS services that we removed from the launch daemons directory, right? Because before we just wanted to execute bash without interference, but now we want to have a full iOS system running with all its services. So we want to bring them all back. We want to support more than a single CPU and an interrupt controller. We want to support more iOS versions and more iOS devices, including ones that use KTOR and PAC. But since we made no kernel patches, then we expect that supporting more versions will not be a very big challenge. We want to write more GDB scripts and Ghidra plugins to make the research simpler. And the main motivation for starting this all was to conduct security research, and we intend to do just that. All right, so if you found this project interesting and useful, you can find it on GitHub, and better yet, you can contribute code to it on GitHub. Have a look at the issues to tackle posted on the GitHub repository. If you indeed found it interesting, you can find more research details, which I did not have time to present, and other research projects on our blog and on Twitter. And that brings us to the end. I'd like to thank you all for your time and attention today. Thank you. Any questions?
Sorry.
You've mentioned that when Mr. Chang ran his emulator on iPhone X, he didn't have any SMC calls. So does this mean that the sole purpose of the secure monitor is to implement the KPP? Is there no secure world in iPhone?
Well, the thing I know about the secure monitor that it implements KPP. There might be other uses for it that I'm not aware of, but this is what I was able to gather about the secure monitor.
Okay. Thank you.
Thank you for your talk and your work. Do you expect any legal difficulties with Apple?
Well, I don't think so. Well, I don't think that what we did was illegal, and I don't think they're going to pursue anything regarding it, but I'm basing this because on the fact that there are a lot of virtualization solutions out there, not for iOS, but let's say for Mac OS, right? There are a lot of solutions that implement virtualization for Mac OS, and they're not pursuing any legal action for these projects. And I wouldn't see why they would do it, but the answer is that I don't know. Maybe they will.
I wanted to ask if you have any kind of a timeline when the next steps might be happening.
So we're starting to work hard on making this happen, but it still involves a lot of research, and it's not just like implementing features one after the other. We have a lot of good ideas how to implement these new features that I was talking about, but since it's a research project and we are not sure what will work and what not, then it's hard to say what timeline. But I can say that we are working on it, and we expect to advance with it soon. All right, thank you very much.